We would like to study some of the special graphs, and I have numbered them. We have already talked about simple graphs. So when a graph is simple, if it does not have loops and does not have parallel edges. This is an example. So here we don't have loops and we don't have parallel edges, so it is simple. If we have a directed graph and it is simple, sometimes there is no need to put labels on the edges, because we can refer to any edge by its endpoints. And since the edge do not have an arrow, so order is not important. So we say the edge UV or we say the edge VU. So we can write it as a set of two elements representing the edge. The other type of special graphs are complete graphs. So when a graph is complete, first it should be simple, no loops, no parallel edges, and if it has n vertices, then between any two vertices there is an edge, whose set of edges contain exactly one edge for each pair of distinct vertices. The symbol for complete graph is capital letter K, and the number of vertices of this graph is represented as a subscript and K, which is Kn. So if n is 2, then we have a graph of 2 vertices. If n is 3, then we have a graph of 3 vertices. So how to draw the complete graphs for K2, K3, K4, and etc. For K2, we have only 2 vertices, and this is the only edge between them. So this is the picture of, or the diagram of K2. Now for K3, it has 3 vertices, and to make every 2 vertices adjacent, or they have edges, then we draw these edges and it forms a triangle. Now for K4, we have 4 vertices, and to make an edge between every 2 vertices, then these are the vertices and connecting by these edges, and don't forget we need also these edges. Now for K5, number of vertices 5, and we need to draw between any 2 vertices an edge. So let's go for V2 for example. So I need to draw an edge between V2 and all other vertices. So this is an edge, another one, third one, and fourth one. And for V2 is similar, and for V5 similar, and notice that some of the edges are shared, okay, between vertices. One observation here, since there are no parallel edges and no loops, and then we can determine the maximum number of edges incident to any vertex. If this is K5, so the number of vertices is n equal to 5, then for this vertex, it is maximum adjacent to 4 vertices. It cannot be adjacent to itself. So this is 1, this is 2, this is 3, and this is 4. So here we can say that for a simple graph, the maximum incident edges for a vertex is simply n minus 1. After simple graph and complete graph, we have bipartite graph. Bi stands for binary, 2, and partite stands for partition, which is division. In sets, we say partitions of sets of 2 or more sets if their intersection is disjoint, no intersection between them, and if you take the union, it gives you the universal set. Now here we are talking about 2 sets. So what is a bipartite graph? It says it's a graph that if you can partition the vertices into 2 subsets, V1 and V2, and one of them could be empty. No intersection between them, so you have to leave every vertex of the graph in one of them, and their union should be the set of all vertices. So that means every vertex should belong to one of these 2 vertices. This is condition 1 for bipartite graph. You divide the vertices into 2 sets. Every edge in the graph, and you know that edges have 2 endpoints. In the bipartite graph, for every edge, one endpoint should belong to one set, and the other endpoint should belong to the other set. This is a situation of a bipartite graph. So this is one set, V1, and this is another set, which is V2. And notice the edges are between the vertices in different sets. So there is no edge between any two vertices that belong to the same set. Let's go over some example and check whether in these examples the graphs are bipartite or not bipartite. We are going to draw a graph now that consists of six vertices. This is the first vertex, this is the second vertex, this is the third vertex, and here we will have the fourth and fifth and sixth. And we will give them labels. So this is V1, this is V2, this is V3, this is V4, this is V5, and this is V6. And now we will connect them with the edges. There is an edge between V1 and V2. There is an edge between V2 and V3. There is an edge between V1 and V6. There is an edge between V6 and V5. There is an edge between V2 and V5. And there is an edge between V5 and V4. And finally, there is an edge between V2 and V4. Now the question is, if this is G, is G bipartite? So if you want to discover whether it is a bipartite or not, then you have to divide the vertices into two sets, V1 and V2. Before I proceed, this is one way of drawing vertices. There is another way of drawing vertices by a circle, and the label is written inside. So this is one way to represent vertices, and this is another way to represent vertices, dots with the labels outside or close to them. So we need to divide now the vertices into two sets. On the right hand side, here I will have V1, and here I will have V2, and I'm going to use two different colors. Now you have to do it by trial and error. So you have to put some vertices for the green color and some vertices for the blue color. Let's go for this edge. Since these are adjacent, then V1 should belong to one set and V2 should belong to the other set. So I will put V1 in here. Let us use different color, so I will put V1 here, and we will put V6 on the other side. And remember that there is an edge between them. So there is an edge between these two. So now we have covered this edge. Now let's go for V1 and V2. Since V1 and V2 are adjacent, V1 is already here. So we need to put V2 on the other side. So we will put V2 in the other side, which is in V2. And there is an edge between these two. Between these two edges, there is an edge. And this edge now is covered. Let's go for now V6, V5, which is this one. Since V6 and V2, then we will put V5 and V1, and we draw an edge between them. And now we are covering this edge. Now V2 and V5, which is for this edge, also we can draw them since they are on different sets. So we can draw them, so this is also covered. Now V3, since it is adjacent to V2 and V2 is in the set of vertices V2, so we have to draw a 3 in the other set. And we draw an edge between V2 and V3. And we have covered this edge. Now V4 and V5, there is an edge. So 5 is already in V1. So I have to put V4 in this vertex. So in this vertex set. And then we draw an edge between V5 and V4. And this covers this edge. Now we will come to the last edge. This one. Now notice it is adjacent between V2 and V4. So if you put that one between V2 and V4, then they are adjacent. So this tells you that G is not bipartite. Why? Because two vertices in the same set are adjacent, so it is not possible that this graph be bipartite. There is another way without drawing. See, we are drawing. There is another way to do it by using colors. Since it is binary, so each vertex should belong to one set. So we will give a green color to one set and a blue color to the other set. So, for example, we will start with V1. V1 is in, we will label it as a green. And since R is labeled as a green, any other adjacent vertex should be blue. So this should be blue and this should be blue. Now since V6 and V5 are adjacent, so V5 should be of green color. And see, there is no conflict between these two. Why? Because these are belonging to different colors. This is a blue and this is a green. Now for V4, it should be blue. Why? Because it is adjacent to a vertex that has color green. And also for V3, it should be green here. Why? Because it is adjacent to a blue labeled vertex. Now what about now this edge? Notice now this edge, it has one vertex of a blue color and the other one has also a blue color. So there is a conflict. So this edge cannot have both endpoints with vertices with the same color. So we can use coloring also for proving as well. There is no need to draw it. You can just simply draw it. For another example, we will have these vertices, 1, 2, 3, and here we will have one more, and here we will have one more. So I'm just drawing the graph, and here also we are going to have one. So now let us draw the edges. There is an edge between these two, there is an edge between these two, and between these also there is an edge. Between these two there are edges, and between these two there are edges, and we have an edge from between these two vertices, and there is an edge here and there is an edge here. Okay, we will give them now labels. So I will give them just simply 1, 2, 3, 4, 6. This is 5, 7, 8, and 9. So the question is G bipartite? So we can prove this by using coloring. So I'm going to use two colors, green and red. So I will start with vertex number 1. Now if this is a green, 9 is adjacent, 2 is adjacent, so I expect that 8 is a green and 3 also is a green. Now 3 is adjacent to 6 and adjacent to 9 and adjacent to 4, so I expect that 5 should be also green. Now if I go to the other color, now 1 and 9, so this should be red, so there is no conflict between these two. And now we will go to, this is also red, and this is also red, and this is also red, and this is also red. By testing each edge, we will find that the endpoints will have different colors. So for example, this edge, red and the green, different colors. This edge, green and red, different colors. Now we want to draw it. So if you want to draw it, then you have to put, let's say, V1, and we will put 3, and we will put 5, and we will put 8 in one vertex, which is for the green color, which is V1. And now for V2, then we need to put the other vertices. So we will put 2, and we will put 4, and there is 6, 7, and there is 9. We need to draw now edges between them. So there is an edge between 1 and 2. There is an edge between 1 and 9. So it's going to be a long line. And there is an edge between 3 and 2. So we are covering now. We are covering this and we are covering this. So 2 and 3, we are covering this edge. 3 and 9. And between 3 and 6, 6 and 5, 3 and 4, 4 and 5, 9 and 8, 8 and 7, and we have 9 and 5. So the graph is bipartite, so we say yes, it is bipartite. What is a complete bipartite? A complete bipartite is a simple graph who is bipartite, so it should be bipartite, and whose every vertex in one set is adjacent to all vertices in the other sets. So when you partition the graph into V1 and V2, if every vertex in V1 is adjacent to every other vertices in V2, then it is called complete bipartite, and M represents the size of the first set and N represents the size of the second set. This is an example of a complete bipartite graph. So the symbol is K32. 3, it means the first set has 3 vertices and the second set has 2 vertices. And C, every vertex in V1 is adjacent to all vertices in V2. So V1 is adjacent to W1 and W2. V2 is adjacent to W1 and W2. And also V3 is adjacent to W1 and W2. So we say that this is a complete bipartite graph. If we ask you a question, if you have a complete bipartite graph, then how many edges does it have? So it is a very simple question. The number of edges it has is the multiplication of M times N. So this is like a multiplication of 2 sets. So we have simple graph, we have complete graph, we have bipartite graph. As in a special case, we have complete bipartite graph. Now we come to cycles. So a cycle, this is the symbol for cycle, and N represents the number of vertices. And the minimum number of vertices for cycle is 3. So what is a cycle? It consists of N vertices, V1 up to Vn, and edges between every 2 subsequent vertices. So if there is an edge between V1 and V2, between V2 and V3, V3 and V4, and it goes up to Vn, and then Vn goes back to V1. Then we say that this is a circle or a cycle. We call it a cycle, or we call it, and sometimes it is called circuits. This is C3, and as you notice, it forms a cycle. This is a cycle. This is C4, so this is also a cycle. So these are adjacent vertices, and there is an edge between them. So if this is V1, V1 goes to V2, V2 goes to V3, V4, V5, and returns back to V1. So they are called cycles.